Folks, we are rounding third and heading to home here in section 6.5. We have two more example problems to go. And I'm going to be honest with you, this example might be one of my favorite examples of all time. It's got a couple of my favorite things in it. It's got, let's see, heavy metal. It's got Cleveland. And it's got screaming babies. I mean, what more could you ask for in a problem? This is incredible. Okay, this is a problem that is no longer using one of our exponential functions, but this one's using a logarithmic function. And we're going to need the following relationship here on this one. Sound level as a function of intensity equals 10 times the log base 10 of intensity divided by 10 to the negative 12th. Holy cow, what does all this stuff mean? Well, this is a scale for measuring sound intensity or sound pressure, and it's a function of intensity. We're not given the intensity, we're given the sound level. Okay, so what we have to do is solve for the intensity I and then compare Motorhead to the Screaming Baby. Okay, so we have basically two things we have to do here. The first thing we have to do is determine that sound intensity level for Motorhead. So let's go ahead and start here with Motorhead. And we're going to determine their sound intensity by taking what we know from Motorhead, and that's that they once reached a decibel level of 130. Okay, and that's the output of this logarithmic function. That equals 10 times the log base 10 of sound intensity. I'm going to label that intensity of M, meaning Motorhead, divided by 10 to the negative 12th. So we need to solve for sound intensity here, and that's buried inside this logarithm. So the first thing we need to do is get rid of this 10. We're going to do that by dividing both sides of this equation by 10. And that's going to give me the following. 130 over 10 is 13 equals the log base 10 of I sub m over 10 to the negative 12th. At this point, I'm going to rewrite this one as an exponential. I've said this enough times now that I hope it's starting to stick. Any logarithmic equation can be rewritten as an exponential. So this means that 10 raised to the 13th power equals the sound intensity divided by 10 to the negative 12th. If you multiply both sides of this equation by 10 to the negative 12th, you're going to get 10 equals the sound intensity of Motorhead. Hey, that's pretty exciting. I bet you never thought when you signed up for college algebra that you would know what the sound intensity was for Motorhead. That's pretty exciting. Well, we're done with Motorhead, so let's now talk about the baby. Okay, the Screaming Baby has a sound pressure or sound level of 115 decibels. Sounds like it's pretty close to 130. So maybe there really isn't that much difference between Motorhead and a Screaming Baby. So we're going to set this one up the same way. I'm going to go ahead and pause the video here in a second and go ahead and solve for this sound intensity while the video is paused. But it's going to be 10 times the log of intensity of the baby divided by 10 to the negative 12th. I'm going to solve this equation the same way I did for Motorhead, and I'll show you what that is in just a second. Folks, I'm almost done solving here for the sound intensity of the baby. I've got 10 raised to the 11.5th power equals the intensity divided by 10 to the minus 12th. When I multiply both sides of this equation by 10 to the minus 12th, I'm going to get 10 to the negative 1/2, or negative 0.5. If it's okay with you, I'm going to write it as a exponent just so we can practice a little bit with exponents. That equals the intensity of the baby. Now, how did I know it was 10 to the negative 1/2? Well, when I multiply two powers that have the same base, I add the exponents. 11.5 minus 12 is negative 1/2. So this 10 to the negative 1/2, that's my intensity of the baby. Now, what did the original question ask? Let's scroll back up and take a look at that. Try to determine this by investigating how many times greater the sound intensity is of Motorhead than a Screaming Baby. When we originally looked at the sound levels, those decibel levels didn't look that different. But now we're actually going to compare the sound intensity levels, and we're going to look at a ratio. Okay, so this is our final answer here. We're going to look at the ratio of the intensity of Motorhead over the intensity of the baby. And the intensity of Motorhead was 10. The intensity of the baby was 10 to the negative 1/2. Well, let's see. If properties of exponents, this is 10 to the first. When I divide two powers that have the same base, I subtract the exponents. 1 minus negative 1/2 is 1 plus 1/2, or 10 to the 3/2 power. When you plug that into your calculator, folks, you're going to get an answer of about 31.6. Holy cow. That tells us that Motorhead is 31.6, has a sound intensity 31.6 times greater than the baby. So I guess Motorhead has beat the Screaming Baby in this competition. As promised, we have 5 examples here in section 6.5, so let's take a look at the 5th and final example. Information entropy. H is a measurement of password strength. In general, the higher the entropy, the stronger the password. Folks, one of the reasons why I think this example is interesting is because it has a lot of words in here that we probably have no idea what the heck they mean. Like information entropy. If anybody's heard of that, well, then that and $1.50 will get them a cup of coffee. So we have another logarithmic model here that we're going to use, and this one is given to us in the notes. It says entropy H equals some value L times the log base 2 of n. And let's talk about what each of those values mean. So in this model, n is the number of possible symbols for each character in the password. Well, let's talk about that for a second. If a 7-character case-sensitive password is comprised of letters and numbers only, find the associated information entropy. Well, let's take a look at what n will be. So we can include numbers. That'll be 0 through 9, so that's 10 different numbers. We can include uppercase letters, so that's going to be 26 of those. Last time I checked, there's 26 letters in the alphabet. We can also use lowercase letters. There are 26 of them as well. And that's a total of 62 different characters that we could include in our password. So what is this value, this other value in this equation, L? Well, that's the length of our password. So what we can do now is calculate the information entropy of a 7-character password given numbers and both uppercase and lowercase letters. So that's going to be H equals 7 times the log base 2 of 62. And this is straight plug and chug into your calculator, and you're going to get a value of 41.679. So what does that number mean? Well, I'd argue that it doesn't really matter. We're not asked to interpret what it means. I'm guessing that information entropy, the higher that number is, the harder it is to crack a password or guess at a password. But we weren't really asked to do that, so I'm not necessarily going to worry about it right now. What I am going to do, though, is move on to part B. How many possible symbol options per character is required to produce a 7-character password with an information entropy of 50 bits? Well, this one is a little bit different than the previous problem. I'm given the entropy value of 50, and I'm told that I want a 7-character password. We need to find out how many characters that's going to take to get us there. Okay, so this one looks like, well, I have n buried in a log, and I'm trying to find n. If you recall from a couple lessons ago, we're going to need a log splitter to do that, and our log splitter is an exponential. First thing I'm going to do, though, is rewrite this, and I'm going to divide both sides by 7. So I have this equation, 50 equals 7 times log base 2 of n. I want to solve for n. First thing I'm going to do is divide both sides by 7, and that'll give me this new equation. 50 divided by 7 equals the log base 2 of n. So I have n inside a logarithm. I've said this several times. I hope that it's becoming second nature to you. I can rewrite this as an exponential equation, and it'll give me the following. N is going to equal 2 raised to the 50 over 7, or 57th power. When you go ahead and plug that into your calculator, you're going to get an answer of about 141. So if you want a 7-character password with this password strength, you need to have about 141 symbols options for that. Quite a bit more than we had in the previous one, which was only 62 different symbol options. Okay, so there are 3 different types of problems I can ask you with this equation. I can ask you for h if I give you L and N. I can ask you for L if I give you H and N. Or I can ask you for N if I give you H and L. In part C, this is the one option I haven't asked you for yet. How long should a password be if we won't have a certain number of characters and we want a certain strength? So we're going to go ahead and set up an equation that looks like this. If we want an information entropy of at least 60, that means L times the log base 2 of n has to be greater than or equal to 60. So let's go ahead and substitute in what we know. We have n as 94, so I'm going to go ahead and replace this value of n with 94. And what I have is 60 is less than or equal L times the log base 2 of 94. Well, the log base 2 of 94 is a positive number. So if I divide both sides of this inequality by the log base 2 of 94, I don't have to worry about flipping the inequality symbol. So I'm going to go ahead and do that. Oh, not 95, people. What are we doing here? It's 94. Okay, and that's going to give me the following. When I divide that 60 by the log base 2 of 94, I get 9.15, and that's less than or equal to L. So what does our password length need to be? L needs to be greater than or equal to 10 characters. Where did I come up with 10? Well, 9.15, it's hard to have 0.15 of a character on a keyboard, so I have to round up to the next highest integer, and that would be 10. So if we want that entropy value of at least 60, we need a password length of 10 or more. That's it for section 6.5, folks. I hope you've enjoyed this as much as I have. Please stay tuned for whatever comes next in College Credit Plus College Algebra.